Alright guys, I'm going to talk about network protocols here. This is chapter 13. IP terminology, so a little bit brief information here about it. You have the bit, which represents a binary digit, whether it's a 1 or a 0. You have the byte, which is basically 8 bits. Could also be 7, it really depends if it is in parity or not. We have the octet, which is made of 8 bits. Is just another 8-bit binary number. You have the network address, which is designation used in the routing of packets to send to a remote network. You have the IP address, which is a logical address used to define a single host, and the broadcast address, which is used by applications to and hosts to send information to all hosts on the network. So you have one guy sending to everybody. You have the 32-bit IP address is known as structured and hierarchical. It has a major advantage in this scheme, which allows to handle a large number of addresses. We have 3 representations here, so you guys can see the variations. You have dot decimal, you have binary representation, and hexadecimal. We're not going to really touch hexadecimal, just dot decimal and binary is the mostly things you should be concerned with IPv4, which is the 32-bit IP address scheme. So network addressing, the network address basically uniquely identifies each network. Every machine on the same network shares a network address as part of its IP address. As you can see, show like a few classes here. You have class A, class B, class C, and 8 bits of the 4 octets. It's designated for networking for the network address on the class A. Class B, you have 2 octets, and the class C, you have 3 octets. So the network addressing kind of works like this. You have class A, which is basically the first octet from 0 to 127. The class B on the first octet will be from 128 to 191, will be a class B address, and a class C address will be 192 to 123. We'll also have the presentation here in binary, what they will look like, those ranges, as well as a better representation here showing N for network and H for hosts. That's what basically the H here stands for, is how many octets is reserved for hosts. And we also show a representation of the subnet masks for this network. Private IP address, IFC 1918. This is a request for comments that IEEE uses for their engineering papers that come out. IPv4 is one of them. So we call private IP addresses addresses that are used for private networks, like for example 10.0.0.0 through 10.255.255.255, which is a range. On class A, typically is used for private addresses. We mean like businesses or schools or your house. Class B is the same thing. We have one block, which is the 172.16 to 172.31. And the class C, we have the block of 192.168 to 192.168, 255 to 255. I also have here a graph with all the classes. In this little table here, you have the class A, the class B, the class C, and the D and E. D is multicast addresses only, so is only used for routers to be doing multicast addressing. And we also have the experimental bunch, which is class E. But if you look, really the only ones that you should really be concerned is the class A, B, and C. We'll also have a presentation here again with the subnet masks, as well as the CIDR notations. So as you can see, only use 8 bits for the class A address, so it's a /8. For the class B is a /16 because you used 2 octets and each of the octets is worth 8 bits. You also have the class C, which is 24. Also have the number of networks for each of them and the number of hosts for each of them. So with that, we come into the subject of subnetting. So subnetting basically it allows you to make use of these, for example here, as you can see there is a bunch of blocks designated for hosts. It allows you to start making slices of these octets to have like less or more number of networks, or more or less number of hosts. So by subnetting, we're able to reduce network traffic, we're able to optimize network performance, as well as simplify management. So again, we have the masks here. So the slides you just repeat. It gives you a little bit more information. But the main thing about this slide is that it really shows that representation of network, host, 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 network, network, host, host, host. Now, talking about the classless interdomain routing, or CIDR, which is what makes subnetting possible. Basically, it's a method that an internet service provider will use to allocate number of addresses to a company or a home connection. They provide addresses to a certain block size. For example, you have here an example here of a class A using a mask of 255.0.0.0. This means that the first byte, right, over here is used. This first section here of the address, which is the first numbers, the first octet, is used by the regional internet registry. By the INA to provide to the regional internet registry of a region. And then you have the regional internet registry grab this block here and assign to the local registry, and the local registry is then sells or leases to like internet service providers or businesses allocations of IPs on a /22 or 10,024 IPs. So that's basically what this is. This also classless interdomain routing, or CIDR, is basically what allows us to do subnetting. So this is a binary representation of a number. As you can see, 235 is the same thing as 100 times 2 plus 10 times 3 plus 1 times 5, which is the same as 10 to the second times 2, 10 to the 1, 10 to 1 times 3, or 10 to the 0 times 5. So if you add each of these parentheses, you get 200 plus 30 plus 5, which is equal to 135. In binary, this would be a little bit different, right? If you look at this example here, 2 to the 7 times 1, plus 2 to the 6 times 0, plus 2 to the 5 times 1, plus 2 to the 4 times 0, plus 2 to the 3 times 1, plus, and then you have 2 to the 2 times 0, 2 to the 1 times 0, 2 to the 0 times 1, and if you really break them down, and you're gonna have the 128 times 1, the 64 times 0, and so on and so forth, as you can see here. And the result, once you add everything in, it's going to be 168. So this is basically how 168 will look in binary, and this is what 168 is in decimal. So to further clarify how subnetting is, how we look at all these bytes, right? So as we were talking about the octets, right, they have 8 bits. So each one of them represents a decimal number. So the furthest from the left worth 128, or 2 to the 7. The second is 64 or 236, and so on and so forth. You have 28, 64, 32, 16, 8, 4, 2, and 1. And this is how you do a conversion between decimals and binary. You have this other table here showing you how to get 170 decimals. If you have 170 and you put them in binary, this is basically how you add them up. So it's kind of like a light switch, right? So you have all these houses here, they each worth a different decimal number. And as soon as you flip the switch on, which is the number 1, you add to the addition, right? But you always start counting from the right, never from the left. You start always counting from the right. We're not gonna go into subnetting in this course because it is beyond the scope of this course, but whenever you guys do go through subnetting, you guys will understand why I'm telling you you count from the right, not from the left. But this is just a brief overview on subnetting. Subnetting a class C, this is more or less what it looks like. You have only 8 bits to work with on a class C because the subnet mask is working, is basically /24, so the first 3 octets are done, you only have the last octet that you can work. So it's either going to be /25, /26, and so on and so forth, right? So as you can see, the number of ones start increasing on your right side. That means that all those ones here are reserved for networking. So you cannot assign to a host anymore. You can only assign to a host those IPs that are still on the 0 side of things, right? They have not been flipped the switch on the subnet mask. In the subnet mask, there's still zeros. So like this for example, this 248, this subnet will be really 255.255.255.248, right? That's basically what it is. It's a /29. So you only have these 3 houses here, these three bits here that you can use for host addresses. So if you go back here, right, you look at the last 3. The last 3 are 4, 2, and 1. So you only have 4, 6, 7 addresses in this subnet here. So 7 addresses per subnetwork that you can use for hosts. Now, it's actually less because you also have a broadcasting address. And at every subnet you have a broadcast address and a network address. A network address is, as we phrase it up there, right? It is a shared medium, so you're not gonna be able to assign that to a host. And the broadcast address is an IP that the host can use to communicate with all the hosts within the network. So really, you don't have 7 that you can use, you only have 5, because 2 of them are reserved for other functions. So IP addressing types, you have the broadcast address that we just mentioned. If you was on a layer 2, which is the physical layer, like switches trying to do broadcast, since switches use the MAC address, and the MAC address is hexadecimal, this is what a broadcast would look like. On a layer 3, which is where the routers operate, right, and they use its IP addresses, this is what it will look like. 255.255.255.255. That's a broadcast. Unicast stands for it's used to send packets to a single destination, and multicast is when a single source is transmitted to many devices or different networks. We have another representation here. So as you can see, a one-to-one on a unicast, a broadcast is one-to-many, and a multicast is one-to-many. However, it's confined to a group. So multicast is something that is used a lot in routers when they need to multicast to their routers, right? Loopback address or 127.0.1. It stands for your host, basically. Like for example, this computer here, the loopback address will be 127.0.0.1. Loopback has no hardware associated with, allows you to test the IP software without worrying about broken or corrupted driver or hardware. So it basically allows you to troubleshoot your internal problems, right? Not external problems. Also is used for management of routers. And another reason why sometimes you use a loopback address is if you are hosting some web developers developing a website, for example, and they want to test it on their own local machine, this will be where they'll be pointing it to. They'll be pointing to the local host, which is yourself. That's why that is the shirt. There is no place like home that the IT people typically do. There is no place like 127.0.0.1, which is basically your host or your home. APIPA stands for Automatic Private IP Addressing. It's a Microsoft thing. This is not, you're not gonna find this on a Linux box. It's strictly a Microsoft thing. However, if you go to cloud providers like AWS, they typically use the APIPA addressing scheme, not as APIPA, but for in-networking things that they do. It may look like it is, but it's not. It's actually doing something else. So what a APIPA does, right, it's in case you have issues with DHCP or whatnot, it actually allows you to do some networking with the local networking nodes they have on premise. So if my computer is connected to some router that no longer has internet, but I'm sharing the same connection with like 5 other people and we're all using Windows, people in theory allow us to talk to each other even though we don't have connectivity at the moment. But typically what APIPA stands for is to let you know that your internet connection is shut. Internet Protocol version 6 is a newer version of IP and is designated as a replacement for IPv4. IPv6 brings many improvements to modern networking. One of these is that the 32-bit address that we're talking about with IPv4 moves to 128 bits. As you can see, you have the global routing prefix here, which is the first section, then the center section, which is the subnet ID, and then you have the device identifier. The device identifier basically identifies, it is almost like a unique number for the host, right? So if you look here, you increase the address spaces 5 times 10 to the 28th addresses for each person on the planet. Now this is great because you won't need subnetting with IPv6, right? Because it's just plenty of it. Simplify header. It has 5 fields instead of the 12 fields that IPv4 had. There are no broadcasts. Security and mobility features are built in. No fragmentation. It's on the protocol. Can coexist with IPv4 doing migration by using dual stack or IPv6 over IPv4. Right. Here's some other differences. You have the length that we just mentioned, the header size, and some other specs here. You guys can look at this table when you have some time, but it's not really critical that you learn all this stuff for the A+ exam. But this one will be a better one for you guys to look at it. IPv6, as I said, is a replacement for IPv4. Now there is another protocol, which is ICMP-v6, which is used to check if a connection is alive on the other end. In IPv4, this is ICMP. In IPv6, is ICMP v6. That's the only difference. Network discovery, replacement for ARP, or redirect and router. Discovery for IPv4. Multicast listener discovery uses is also a replacement for IGMP v2 for IPv4. So these neat little features are replacing all the stuff that we use in IPv4. This is what the packets look like. As you can see, this is the IPv4 packet under the hood. This is what an IPv6 packet will look like. As you can see, it's a lot less stuff going on, a lot more concise. You have the destination, you have the source, the payload length. It's super easy to look at. And you look at IPv4, it's a bit of a mess compared to the amount of stuff. It has a shortener expression, which allows you to abbreviate some of the stuff. As you can see here, you have these zeros here, so you can abbreviate them into double colons, right? You cannot do this twice though. Like if there was another block here, like this was a 0:0, you cannot do this twice. You can only do this abbreviation once. Here's some other stuff. As I said, you cannot do this. You have to be, yeah, you can do the first time, but the second one you actually have to put those zeros there at least once. So, but it's still, you know, it's a lot less than what it would be if it was the whole address. There are a few types of IPv4. Like we went over IPv4, IPv6 we have unicast, which is the same thing as IPv4. We have the global unicast, which is a single recipient to a routable over the internet, which is something that IPv4 does not have. Link local, valid only for the network segment. You have the unique local, which cannot be routed over the internet, which is basically in your local machine, your local network. You have the multicast, right, which serves the same purpose, and you have anycast, which like multicast, and anycast identifies multiple interfaces, but there is a big difference. Anycast is delivered to only one address, while the multicast will be to many, right? So unicast is a one-to-one of many addresses, right? So you have one and then you have a pool. So the first one that it hits on that pool, that's the destination. It's not gonna keep transmitting like multicast would. Here's how you migrate IPv6 to IPv4. We use the dual stacking, right? So basically you run both at the same time and you use the 6-to-4 tunneling. So you have a router, this PC using IPv6 in the network, and then it sends to a router that has the dual stack, and then it goes in through the IPv4 networking. It goes to another router that has the dual stack as well, and it does the little conversion and sends it back to an IPv6 person. So the 6 dual stacking is the most common. Basically, the way we're currently doing this, the 6-to-4 tunneling is useful to carrying IPv6 in a Korean IPv4 network. Needs the dual stack routers, as you can see here, and NET is likely to cause problems. NET is something that it stands for Network Address Translation. It's a little bit beyond the scope of this course, but suffice it to say that it was something that it was made so that our private addresses was able to communicate to the internet with a limited number of public addresses, right? Remember when we're talking about the IP schemes here, right? If you go up here, So these guys, right? They sold so many IP addresses to businesses. So like a business will have 2 or 3 public addresses, and then they use like the whole internal networking. Like let's say you have 300 computers, and they have access to 2 public addresses, which so net allows you to do that, to use those 2 public addresses to communicate over the internet and get results back to your internal networking, which is coming off those public addresses. So it's a way for people to not need to have an individual IP, right, coming out of an internal network to go over the web to browse some website, right? So you use net as a translation between public and internal addresses. IPv6 does not have that because it's not needed. The obvious reasons. You have what, 5 times 10 to the 28th number in addresses. So I mean, that's a lot of addresses. So let's go back here. Address resolution. We have ARP, which finds the hardware address of a host from a known IP address. In IPv6, the similar process would be the neighbor discovery protocol, as we went over in a previous slide. Regardless of which address is stored in cache, if the address is not in the same subnet, then it sends to the next router, and so on and so forth. Right? He's going to keep doing it until he finds that one that he's looking for. So this is more or less what it looks like. So I need Ethernet address 10.1.2. So this guy is gonna shoot over the network. Hey, I need this address, and then basically this is gonna be a broadcast that is gonna send. It's gonna go to every single host, and to the host that actually is that guy, is gonna be like, yay, I'm that guy. This is my network card, right? Basically, this is my MAC address. And that's why sometimes we call it an ARP table, right? When you're trying to figure out all the physical addresses everywhere, that's what an ARP table is for. Another thing to keep in mind is that switches kind of work off the physical addresses as well. So sometimes if you want to identify where a specific device is plugged into a switch, you would go locally on your computer. Let me just show you guys. Go to CMD here, CMD, and you go ARP. What is it? Dash A, ARP, there you go. So there are several addresses that I have here locally, right? And then you have these guys, like over here. This is my ARP table, right? So I'll grab the IP that I want, that I'm looking for, and then I'll go on the switch and I'll match. Okay, I'm looking for 10.0.0.232. So I'll go on the switch and I will match up to their table, the physical address table, and then I'll find which physical port on the switch the device that I'm looking for is. So that's something you guys can do as well. I know we spoke a little bit about DNS, a little bit under the surface, and these are the same slides that I had on the chapter 11, which I corrected. I think it belongs more on this chapter. So basically, DNS it serves to basically make IPs into human readable addresses, right? So you have a host name or name of the device. When you add a domain to that, you have the host name plus the domain. Then you have the FQDN, or the fully qualified domain name, right? Every organization typically has a domain. Like for example, Broward College is broward.edu. It could be any other device connected to it. Let's see, you have PC number 15, right? So pt15.browser.edu, that's the fully qualified domain name of the specific device. Windows have something like that built in called Windows Internet Naming Server. It's a Microsoft implementation of the NetBIOS or NBNS. Most likely, you're not gonna see much since in 2003 that kind of started being phased out, but it's still there. Like if you use Windows Active Directory, you're gonna see the protocol going back and forth because it's still part of the naming system that they have in Active Directory. Also, for a lot of integration between Linux and Windows, for example, Linux Samba services, that allows for some of the integration. It uses the NetBIOS addressing scheme for that as well. But that's basically what NetBIOS is, right? It's that Windows addressing scheme. So host file, and the reason we're gonna talk about the host file is because on the process of trying to get name resolution for a website that you're trying to get to, the first thing that your computer does is hit your host address. Now, independent of the operating system that you have, that is a host file on your computer. This allows you to set static entries for IPs versus URLs locally. So you could even use this to prevent somebody from going to a legit website. Like for example, you work for yahoo.com and you don't want excuse me, you don't want your employees to go to google.com for some reason, like the sales department, right? You don't want the sales department to do that. So you set up some group policy in Windows and you make sure that all those computers in sales, whenever they hit, you know how you have it over here, www.yahoo.com, it would be like www.google.com, and then you put the Yahoo IP instead, right? So every time those computers try to query to go to google.com, instead of going to google.com, your computer is going to take them straight to the IP address of Yahoo. Now, as we go through DNS, you have the different levels of the domains, how the address works. The first thing you have, the very top of the chain here is the root domain, which is the dot. After the dot, you have the top level domains, which will be your mil, your int, your gov, your edu, your com, your net. Then you have the second level domains, which will be what the company bought, right? In case of Broward.edu, it will be Broward. And the subdomains, which will be basically the identification of the precise service. Like, for example, www means that you're trying to hit a web server, right? FTP means that you're trying to hit on a file transfer protocol server. So basically that's what that is. Oh, correction here for the subdomains. Subdomains will be something extra besides Broward, right? So Broward will be like the student email. You have mail.broward.edu, so mail will be equivalent to a subdomain. And the www will be the host name. This is how DNS works. I have a map here, and let's go over the components as we were saying. The end user, the first thing they're gonna do is they're gonna try to hit the host file. Let's say they're trying to go to this website, example.com, right? So they hit the host file doesn't have an entry for it, so the first thing it's gonna do is that the end user is gonna hit the DNS resolver. Once he hits the DNS resolver, which is your internet service provider, you're gonna send the query to the DNS root domain server, which is that dot on top of the chain, right? So once that happens, the root domain server is going to be like, all right, so .com is this top level domain. This is the IP. So now we're going to query the .com, which is the top level domain right here, right, about example.com. Example.com is gonna, then the .com is gonna shoot back to you, and it's gonna let you know where example.com, now it's a little bit more compound, is located at. So now you're gonna shoot, so it's telling you here that example.com is on Route 53, which is an AWS DNS service that they have. So we're gonna shoot up to Route 53. Hey, Route 53, tell me where it is, www.example.com. Oh, this is the IP address. So now you're gonna have the answer from to your internet service provider, which is gonna shoot the the answer to your host computer. And once that happens, your computer is gonna resolve to that web server, and you're gonna be able to get whatever you're trying to get. There are a few elements to DNS. First of them is the A record, which basically maps a domain to an IP address. You have the equivalent for IPv6, which is the four A's, right? A. It means that it maps an IPv6 to a domain to an IPv6 address. NS stands for name server record, which is basically delegating a zone to a name server. For example, Broward.edu has a name server, so everything under, like for example, www or FTP or mail.broward.edu, it's under a name server. So that's basically what it is, the location of that name server. A pointer record maps an IP address to a domain name. CNAME is a canonical name, which is basically a nickname to a site, to an A record. That's basically what CNAME does. MX is the same of these. Like, no, it could be an A. It would be equivalent to like an A record is to an IP. It would be an MX would be equivalent to a record of a mail server. Address assignments. Address can be assigned to an IP device in three different ways. You have static assignments, you have dynamic assignments, and stateless address configuration. So static assignments is when you manually go to the machine and you put all the configuration on the network interface card. Dynamic assignments is when you have that stuff happening automatically. A way you can have that happening automatically is if you have a DHCP server. Stateless address configuring is a private IP address chosen by a host itself through a communication with a local subnet. IPv4 is the only one used when another method fails. IPv6, this is a link local address and is assigned even when a node also has a global address. So Dynamic Host Configuration Protocol Server, or DHCP, receives a request for IP information from the DHCP client using a broadcast. So client gets on the network and shoots a broadcast. Hey, who's the DHCP server? And then the DHCP server will reply. And then they make a whole transaction and you have a device getting an IP address dynamically. So it has unicast will be sent to the designated DHCP as a router knows which to send, and direct broadcast to multiple servers. As you can see here, unicast. So this guy broadcasts on a router, and the router does a unicast to the server, while you have broadcast to the router, and the router knows there's more than one server, so he's going to broadcast it as well. This is a little bit more of more or less how it works. right? The process here. Oops, here you go. If you look here in the section, so host gets on the network, host has no IP, right? So he does a discover. He sends a UDP packet, right, on port 68 and reaches the server on port 67 UDP. And the DHCP is gonna send a DHCP offer. Hey, I have this IP available. Would you like that? And then the guy with no IP, right? The new host is gonna be like, yes, I will use the IP you just gave me. I agree. And then the DHCP server is gonna send an acknowledgement, letting him know that he has assigned that IP to host A. That's basically more or less how it works, the whole communication. There are other aspects too, is like how much a lease will last, because this is a lease really, right? So there's gonna be a time that this client is gonna have to talk to the DHCP server again in order to renew that lease. Now some other elements here. This is actually, I pulled this out from Windows Server machine because I think it's the easiest way for you guys to visualize how things are. So this is an address lease screening. This is more or less what it looks like. For example, this guy got assigned this IP, right? And then the lease expiration, it gives you a date here. So whenever it hits that time, this guy, if he's connected to the network, he's going to have to contact the DHCP server again. Now, typically, the IP will stay the same. However, sometimes, from time to time, the DHCP server, depending on how long the whole communication happened, and this happens more with internet service providers, is that because they also use DHCP to provide dynamic IPs to people. From time to time, depending how fast another IP requests an IP, you might not get the same IP address back. But typically, for the most part, I find that DHCP assigns the same IP address. It just keeps renewing that. Another thing here, there are some DHCP options you can have. For example, in this setup here, you have a imaging server. I remember talking about Pixie booting for people that want to install the operating system via the network. So this would be settings that you would set for the DHCP to have Pixie boot enabled. This is one. If it is enabled on a Linux box, so a Linux box hosting an imaging server, right? And it also points the IP address of the imaging server, right? So this will be something that you can do, that you can set up on your DHCP. So if you need to do imaging, this will be the way you'll be doing it. Now there are different types of servers that you can have with Pixie booting. But this is the most common one. DHCP client and DHCP relay and the server. This is more or less how the whole thing works if you have a relay, which is basically the same thing. Here you just have a man in the middle here that does the communication between the two. Let's go to the next slide. Troubleshooting TCP/IP settings problems. So if the DHCP is enabled but you assign an IP address or link local range, it means that the client can contact the DHCP server. So things you can do is check your network connection to make sure that there are some other issues that are causing the DHCP server to not to respond. So if you check your cable and everything is fine, maybe that is something going on with the server. It could be also misconfiguration on your part. Maybe you assigned a static IP that it's not even matching the subnets, or you maybe have more than one interface card, network interface card, and you plug to the wrong one. That's another thing you could do. Um, another problem you be if the client's IP address or subnet mask doesn't match the subnet it's connected to, you won't have network connectivity. Or if the clients have duplicate IP addresses, it can lead to a failed connection. That means that you're most likely gonna have to do an IP release and renew on that. Well, this can happen a lot of times if it is you have like two computers, one of them it's been off for like a week or two, and then you put it back on, and it's trying to renew a DHCP lease that was expired, and for some reason something happens, some other computer already grabbed that IP that you're trying to renew the lease with, and you could cause a conflict, and you might have to do a release and renew on the IP. I've seen that happen before a few times. An improper default gateway. This means that a default gateway basically is a router or a proxy that you have your network interface card talk to route your traffic. If you have a bad one in there, a proper one set up, then you're not going to be able to communicate with your local subnet. A host can also have multiple network interface cards, as I mentioned, and you may have the wrong one configured, or also that could make the configuration more complex depending on the type of addressing that you're doing on those cards and where they're going to. Improper DNS server settings will keep you from resolving domain names. So if you're trying to go to google.com and you can't, but you can ping the IP address of google.com, then the problem is name resolution. Configuring IP settings. Controllers use IPv6, IPv4, and IPv6 to have separate settings for each. They can have different DNS servers and even different manual and DNS server assignments. You can configure your operating system to use DHCP by default, but applies static settings if it can't find the DHCP server. If you assign a static IP address, you must also assign a subnet mask and a default gateway. If the operating system supports, you can assign a manual DNS server via the DHCP or use a static IP for it. If the manual assignment of the IPv4 address, you must manually also configure the DNS servers. IPv6 allows network neighbor discovery protocol discovery of the DNS servers even without the DHCP server, provided a local IPv6 router is configured to send the DNS advertisements. Network interface card can have multiple DNS servers, whether as part of static or DHCP configuration. This allows you to maintain DNS functions even if the primary server is offline or unreachable. A single adapter can have more than one IP address. If you assign an IP address remotely, such as changing settings in a device via a web interface, you need to connect again using the new IP address. TCP/IP protocols. So in short, TCP connection is connection oriented, while UDP is connectionless. That means that there is a handshake when you do the TCP connection, right? Because you want to make sure that if I'm sending data somewhere, you want to have an answer. It's kind of like certified mail. Like you send a certified mail to someone, and then the post office lets you know that, hey, that person got your letter. While UDP is just like sending a regular first class letter. You don't have an answer if the person got it or not, unless the person gives you a call. And this is pretty much the same thing. Now, TCP is it's reliable, is as I said, connection oriented. He also has a higher overhead because of all, the stuff. It has acknowledgments, is sequenced, and while UDP is unsequenced, is unreliable, is connectionless. It has a very low overhead and no acknowledgments. Just keep sending. You don't really care if the person is getting it. It's kind of like, like those spam mail that you get on your mailbox, right? People just keep sending you that stuff. They don't care if you got it, right? Uh, so a few things here. You have TCP is reliable, right? It guarantees that all data is successful delivery to the host. If the segment fails arrived, you will figure it out where it failed and it's gonna send a segment again. Error correction, the TCP will have a checksum that allows it to find the error. While UDP also has a checksum, but the checksum, what it does is allows you to just move on. That's basically what it does. Flow control, as part of the acknowledgement process, the remote host can regulate the rate of data flow. This keeps the slow recipient from being overwhelmed by high-speed transmissions. Right, so you're sending, and then you're gonna see a little bit better here if you look at it. You have a SYN, and then you have a SYNAC. This is the connection oriented, how it looks like, and the connection established, and then the data transfer begins. So going back to the sequencing stuff and flow control, if you look over here, flow control provides a means for the receiver to govern amount of data sent to the sender, right? So if you look at it over here, right, you will see, so this guy is transmitting, right? And then he has a buffer, the receiver, and the receiver, hey, listen, I got too many of your packets. Please stop sending it for now. Once those packets are processed, the receiver is gonna say, all right, go, keep transmit again. And that's what's gonna happen, right? So this is what flow control is to allow for a buffer between transmissions, right? You also have something called windowing, right? Which is how much data the receiving host advertises that it can receive before it sends an ACK. So it's just like basically, hey, listen, I can handle 1460 bytes, right? So this guy sends, and then after 16 kilobytes are processed, then it's gonna send an ACK for the sending host to proceed in sending. Right, that's basically, they work hand in hand, both of them. This is what UDP and a TCP format protocol look like under the hood. Network ports, as shown in the previous slides, UDP and TCP, you have a source and destination port as part of the packet. This specifies what port the application is listening, and the destination, as well as the port that the host is sending the packet, is listening for replies. So if you have a client is, like a computer, and the computer is trying to hit a website, they're gonna do a GET request, right, on port 80 typically, or port 443, either or. So whenever your request is sent, your destination port is gonna be either 80 or 443, which is either HTTP or HTTPS. And then the server, right, that hosts your website, which is a web server, is gonna be listening on those ports, either 80 or 443. And once he grabs your request, you're also gonna grab a port that your computer has, that your browser is using to listen to the reply of the web server, right? In this case, we're having the example here, port 5000. So the web server is gonna send a response to the host, the client that requested on port 5000. Um, TCP and UDP protocols as 16-bit use 16-bit ports. The range of those ports, the amount of ports about 65,536, which are not shared, which means that you can have your host listen on UDP and TCP at the same port, and it can both will probably be doing different things. What you cannot do is have two hosts, two services in your host listening to the same port, or you're gonna have issues. Port ranges, there are different types of port ranges here. You have the system ports or well-known ports, which is 0 to 1023. You have the user ports or register ports, which is 1024 to 49,151, and you have the private ports, which is basically the rest. These are used for like special services or temporary purposes. This table here is very important that you guys memorize for the network plus to the A plus exam, because they will test you on those. So you have like several different services here. Let me see. Yes, I set it up like that. So several different services here, the type of protocol that they use, right? And these are the ports that those protocols live in, right? And what those services are for. So some of those are used for remote access protocols. This would be Telnet, SSH, RDP, VNC, HTTP, or SNMP. This guy, and this guy are command line, while RDP, VNC, and HTTP, they're typically graphic. However, HTTP could also be used for command line as well. HTTP is when you have a remote desktop via browser, typically, or some browser wrapper, one or the other. Authentication protocols, you have radios, TCAX Plus, Kerberos, and 802.1x, as well as LDAP listed here. So radios is designed for dial-up connections on private LANs, however, is also used very commonly to integrate with LDAP as well for authentication. TCAX Plus is a variation of radios used by Cisco. Kerberos is what Windows Active Directory uses, as well as LDAP for authentication. It's how their whole authentication scheme works. 802.1x, it's used to authenticate connections to a Ethernet switch, wireless access point. It's a protocol used by Wi-Fi hotspots operating enterprise mode as well. And LDAP is the lightweight directory access protocol, which is basically a directory service. Now, LDAP is the open source version, while Microsoft has what they call Active Directory, which is a lot like LDAP. They both use Kerberos to operate for authentication purposes. We have file sharing applications. You have the FTP, which is File Transfer Protocol, which is the oldest, which is super vulnerable as well. If you're going to use FTP, make sure that you're using the SFTP, which is a secure version of it. SMB, which is a Windows server message block used for sharing network drivers on Windows. You have the AFP, which is Apple Filing Protocol, similar to SMB but for Apple computers. And you have the NetBIOS, which is a session layer API rather than strictly a protocol. It's designed to allow various applications to communicate over a network. Now, this is a Windows thing as well, or you can use it for some integration with Windows. Hypertext Transfer Protocol, you have the port 80 TCP, which is an insecure protocol, and the HTTPS, which is port 443, which uses secure socket layer or SSL, or the latest variation of that, which is transport layer security, or TLS, which is the what became of SSL. SSL is not really used anymore. What we use now is TLS, but they often use it interchangeably as far as terms, right? Basically provides encryption over connection between clients and a website. Uses certificate for that type of connection as well. It's very important if you're using SSL and you're connecting or TLS and you're connecting straight to an IP. Most likely your traffic is gonna be you're not using TLS as you should. Most likely your traffic is not going to be encrypted because there is no certificate there to do the encryption. You have email protocols, which is SMTP, or Simple Mail Transfer Protocol. You have the Post Office Protocol, which is POP. You have the IMAP, and you have the MAPI, which is the Messaging Application Programming Interface. Simple Mail Transfer Protocol is used to send emails. POP is used to receive emails, but never used to send emails. IMAP is used for clients to receive emails from servers. Typically, they have a better access to the accounts on multiple devices. POP just sends to one location while IMAP keeps a record on the server. So depending on whatever you log in, you should be able to access all your emails from a single location, from several different locations, while POP is just one location. The MAPI is a Microsoft Exchange email protocol used to send and receive emails from other specific Microsoft Exchange features. So this cuts chapter 13, and we will continue chapter 14.